seminar on combinatorics on words for today. And as you know, this is the 100th anniversary of the death of Axel Thue, who is sometimes regarded as one of the progenitors of the area. And we're delighted today to have Jean-Paul Allouche, who is going to speak on the subject with the title 2A and 7.3. So Jean-Paul.
Okay, thank you. I'm just trying to move my, okay. Thank you very much for this invitation. I'm very pleased and very honored to give this talk. It's called a special event, so I guess I had something special to do. And maybe you will track one or two special things in the talk. So as Jeff mentioned, it's the 100th anniversary of Thue's death. And it was March 3, so the 3rd of March, which is in France at least, and probably in some other countries in Europe, is written 7/3. And this number, whatever it means, might play some special role in the talk. So to begin with, Axel Thue was born in Norway, a town on the city on the Oslo fjord called Tønsberg, on February 19, 1863, and he was the son of Niels Thue, someone involved in ships, and Nicolin Katinka Egga. He died on March 7, 1922 in Norway again, in Oslo. And so this 7/3 or 7/3 or whatever is this anniversary today, exactly 100 years. The way that Thue became interested in math is rather strange. He saw an advertisement someday. Oops, my control doesn't work any longer. That's it. Yeah. Okay. He saw an advertisement for a book by Ellinghorst. The title of the book was On Pendulum's Meaning of Geometry. He ordered the book, believing there was a book in physics about the pendulum. And actually, there was a misprint in the advertisement. It was not on Pendulum's meaning of geometry, but on Poncelet's meaning of geometry. So Poncelet, the famous mathematician or working in mechanics or whatever. And he got the book, he received the book, and it was not at all what he was expecting, but he decided still to read the book. And that's the way he became a mathematician, which is somehow strange. If you want to know more on the biography of Thue, you can go to this site that Jeff Shadid indicated to me at St. Andrews. Okay, so the talk is essentially in two parts, a sort of short first part about the things for which Axel Thue is most known, namely number theory, and more precisely Diophantine equations. And the second part is probably a larger one, and about this famous sequence that we are forced to mention at some point. So here is a result of Thue. I'm not sure what the pronunciation is. I think the right one should be Thue, but sometimes I pronounce it Thue, like in German, or Thue, like it could be in English, you know, like qubit in bridge. Okay, so you take a polynomial, a homogeneous polynomial f with two variables, integer coefficients, irreducible on the rationals, and of degree at least 3. So for any non-zero integer, the equation f of x and y equals c has only a finite number of integer solutions. So this is typically Diophantine equation. Here is an example. If you look at all possible pairs of integers, x and y, satisfying y to the cube minus 2x squared equal 1, then you have only a finite number of such pairs. Actually, the result is a little bit more general, and here's a history of the result between, let's say, 1844 and 1955. You take an algebraic of degree larger than 2, k a positive constant, and if you have an infinite number of rationals P over Q such that the absolute value of alpha minus P over Q is at most 1 to Q to the power K, then this K, capital K, cannot be too large. It's necessarily a small number, whatever small means. So for example, Liouville says essentially that K is at most N. This result of Liouville in 1844. And the improvement by Thue is that K is at most N over 2 plus 1. Siegel, 13 years later in 1921, improved that into K at most is at most N divided by S plus 1 plus S, whatever S be in between 1 and N minus 1. So I'm going to come back to this result a little bit later. So if you try to optimize this by taking the best S, you get something like K is roughly at most 2 root N. The next improvement consisted of putting the 2 inside the root, if I may say. So it was due to Dyson in 1947, and who obtained K is at most root of 2n. And the last and optimal improvement is due to Roth, who proved in 1955 that K is at most 2. And of course, it's optimal because if you take quadratic numbers, for example, fraction expansion or something like this. Okay, and I promised to speak about this result by Siegel. And Siegel said that he tried to read the paper, of Thue, and it was very difficult and essentially incomprehensible. So he tried to write it again for himself, and there were a lot of parameters, and Siegel didn't understand what these parameters were. So what he did is just renamed the parameters and did the job. And by chance, he found a new parameter in doing that Thue didn't use, and this new parameter permitted him to go from n over 2 plus 1 to this value here. And you see that this value, I mean, Thue is exactly for s equal 1. Okay, so Siegel say, okay, it might be a nice result, but it's not my fault, so to say. I just tried to understand something, and I understood better than it actually was. If you want to know more about this, you can either look at a paper by Georges Poitou, a very short paper, just giving some sort of abstract of all these ideas, but there are the 2 Siegel wrote in the Enseignement Mathématique in 1961. And a paper by Catherine Goldstein, Axel Thue in context in the Journal de Bordeaux, Journal Théorie des nombres de Bordeaux in 2015. And again, this site in St. Louis, and of course, a lot of other references to this theorem and to the history of this theorem. So what is interesting somehow is that Thue published 48 papers, 20 were written in Norwegian, 26 in German, but published in Scandinavian journals, and only 2 were published in journals outside Scandinavia and in German. Those last 2 are in Krelle, in the Journal für die reine und angewandte Mathematik. And in particular, Thue got the reputation of being sort of isolated, writing papers in Norwegian that nobody was going to read, and so on and so forth. And not only isolated, but also mathematically independent, which is rather false. And if you go back to this, if I go back to this paper of Catherine Goldstein in the Journal de Théorie des nombres de Bordeaux, you will learn that this is rather false. And he was not isolated at all. Maybe not really with many other mathematicians around him, but definitely not isolated. Okay. Before going further, that is, before going to the second part of this talk, I think that 2 sentences of Thue are important. The first one, he said that for the development of the logical sciences, it will be important to find wide fields for speculative treatment of difficult problems without regard to eventual applications. So just pure abstraction, so to say. And the second quotation is even stronger. the further you move from usefulness or practical application, the more important. Okay, the second part is devoted to Thue, considered of the father of combinatorics of words, or at least one of the fathers of combinatorics on words. As you know very well, there is a famous sequence due to Thue, actually called the famous Thue-Morse sequence, or PTM, Thue-Morse sequence. And I think I have to define it again, although everybody knows about it. So it takes the morphism of monoid mu that on the alphabet, on the binary alphabet 0, 1, and mu sends 0 to 0, 1, 1 to 1, 0, and you start from 0, and you get 0, 1, 0, 1, 1, 0, and so on and so forth. And the reason why Thue introduced this sequence was because he was looking for a cube-free sequence on 2 letters. It happens that this sequence is even more, it's overlap-free. And you can also use, he could also use the sequence to construct a sequence on 3 letters that is square-free. Okay, and he said something like the sentence we've seen there. Further remove operative relation is more important. Actually, what he said about this sequence is there is no way, no real reason, no application, no real application, no expected application, but it's going to be important. Who knows? Something like this. Okay. So I said it's a special event, so we have to do something special, not only mathematics, but also not only computer science, but also whatever else. And so this is digression. If you go to a browser, which I did yesterday or the day before, and look for Thue and mu, I mean Thue, the name of the guy, use the name of morphism. So I type this into Google, and I obtain that there is a city, a commune in Normandy called Thue et mu. Oh yeah, there is a E at the end of mu. And if you go to Wikipedia, I went to Wikipedia, as you see, this is Wikipedia in French, so I went to the Wikipedia in English, and I make it larger. So this is a commune in the department of Calvados, northwestern France. It was established on the 1st of January 2017, merging all the former commune of Bretteville-l'Orgueilleuse, Brouet, Cheux, Le Mesnil-Patry, Puteaux-en-Bessin, and Saint-Croix-Grand-Tonne. Actually, if you go to a map of this part of Normandy, you see you have Caen on the right, Bayeux on the left, in between 2 rivers, la Thue and la Mu, and this Thue and Mu city is exactly between those 2 rivers. Actually, there's a 3rd river down called the Bordel, but I'm not insisting on it. Okay. You can ask why rivers and the picture, I mean, nothing to do with Thue and nothing to do with mu. Quoique, it was not quite unexpected. Namely, if you take this sequence Thue-Morse, so PTM, this is nothing but potamos, and potamos in German, in Greek means, as you know, river. Of course, you know this word because you can find it in hippopotamus, which is the river horse, or Mesopotamia, which means between 2 rivers. Okay, that's explanation of the Thue and mu, isn't it? Okay, let's be a little bit more serious. You know, morphisms like 0 goes to 0, 1, and 1 goes to 1, 0 are introduced some way as morphism of monoid, free monoid, and in the case of the Morse sequence, because it looks like it was the first time it was used, actually not exactly in this form by Thue, that means that you can find that it is not really natural, and maybe there is more natural way of introducing this morphism mu without calling it morphism, by the way. So, for example, you know this product of cosines where you double the argument at each step. So cos x times cos 2x, blah, 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 cos 2 to the n x has a nice closed formula. It's just the quotient of two sines divided by 2 to the n plus 1. So it's sort of cool formula. And if you try to get the same formula, I mean, similar formula for sine, you fail. There is no nice formula for this. So since you have no formula, you can try to get something weaker. For example, what is the sine of this product? Okay, I'm not sure. Is that the difference between pronouncing sine and sine? I mean, S-I-N and S-I-G-N, J-N? Who knows? So if we try to look at the sine of the product of sines, if you take the sine x, then sine x, sine 2x, sine x, sine 2x, sine 4x, and so on and so forth. Let me call plus, put a plus where a function is positive on some interval and minus if it's negative. So you see that if you take 0 pi, I divide it into 4 subintervals. Actually, I should do that in two steps. Anyway, sine of 2x is plus minus in these 4 intervals. And so the product is plus minus minus plus. Haha, plus minus minus plus. Now, what happens if you multiply by sine 4x? Each of the 4 intervals you have there is going to be divided into 2 intervals. Okay, and if you look at this interval, 8 intervals in order, the sine of sinus 4x is going to be plus minus, and so on and so forth. So that because of the rule of sines, each time you had a plus, the interval splits into plus minus, and you multiply by a plus, which is plus minus. And when you have a minus, the interval splits into 2 intervals where the new sign, with a new sign, you get plus and minus, so that with the product, you get minus plus. Am I clear enough? Okay, so at each step, you divide your interval, and the new sign by which you multiply is just an alternating sequence of plus and minus. So you get immediately this sort of natural introducing way of having the morphism, so to say. Okay, actually, this product, sine x, sine 2x up to sine 2 to the x, can be used to get the size of the discrete Fourier transform of the 2 more sequence, and you get n to a power like log 3 over log 4 or something like this. Okay, I'm not going to speak about it here. Okay, another characteristic property of the 2 more sequence, which might be a little bit less known than other properties, is something due to Patrice Sebold and improved by Narad-Rampersad. So Sebold proved in 1985 that essentially the 2 more sequence is the only sequence which is a fixed point of a non-trivial morphism that has binary morphism, not necessarily of constant length, any morphism that has no overlap. In other words, this is written there, the only overlap-free fixed points of non-trivial binary morphisms are the 2 more sequence and its twin, which is the 2 more sequence where you change zeros into ones and ones into zeros. Okay, there was in a Sebold thesis, doctoral thesis in 1985, and there is another proof given by Jean Berstel and Patrice Sebold in 1993. And looking at this, Narad found something better, I mean, an improvement of that, where in 2004, 2005, I'm mistaken, he showed that we can replace the overlap free in the above statement with 7/3 power free. Okay, so you know what a fractional repetition is. 7/3 means you have the word twice, and then 1/3 of the word, the prefix of length, 1/3 of the word. And 7/3 is optimal. Of course, you immediately noted that 7/3, I mean, 7th of March. Again, this 7/3 actually occurs in a sort of very close, very similar way in a paper by Narad-Rampersad, Jeff Shalit, and Arseny Shur, where they prove something like characterization the binary 7/3 power free roots, which can be recognized by some reasonably small automaton with only 15 states that encodes all such words. And in particular, they were able to characterize all these words, all those of these words that are Thue automatic. Okay. In particular, in the paper by Rampersad and Thue, they prove that the least binary 7/3 power free sequence is obtained by gluing in front of the PTM bar, which is the Thue more sequence, the complement of the Thue more sequence. Again, you replace zeros by ones and ones by 0. You glue in front of that sequence 0, 0, 1, 0, 0, 1, and you get the least binary 7/3 power free sequence. Yeah. Okay, let us go to shogi, which is a Japanese chess. And actually, it looks like it resembles a little bit chess, but it's much more complicated and subtle than chess. And chess is already sort of complicated. And in particular, there is something in shogi called the senikite, or maybe senikite, or whatever, which is a specific rule in shogi that forbids repetitions. More precisely, you have a draw, nobody wins, if the same position is repeated 4 times without any check. I mean, you never, the king is never attacked 4 times without involving checks. And in professional shogi, I forgot to say, draws essentially do not count. Either you win or you lose, and if it's a draw, it's just deleted, discarded, and doesn't count at all. And this senikite rule was previously defined by a sequence of moves with 3 repetitions, and the rule was changed in May '83, where 3 repetitions were replaced by 4 repetitions after historical play between Kunio Yonenaga and Koji Tanigawa. Yeah, I forgot to say something. I forgot to write something on the slide, which is that you still can have an infinite game with 3 repetitions. In particular, you can obtain such a game by using a sequence like the Thue more sequence, of course. Interestingly enough, this play between Yonenaga and Tanigawa occurred in March 1983, on the 8th of March. Again, 7/3. Oops, no, it's 8/3. Okay. Of course, the same thing exists in the usual chess. This is a so-called German rule. And it states that if a draw occurs, if the same sequence of moves occurs 3 times in succession, then you have a draw. And there is an old paper by Thue, 1929, who proved using the sequence, which was cube-free, and that under such a rule, infinite games of chess are possible. And the sequence that Thue proposed is essentially, I mean, it's exactly the Thue more sequence. Okay. Now a question of fairness. One of the first papers in this direction, to my knowledge, maybe one of the first papers, is a paper by Palacios Huerta called Tournaments, Fairness and the Thue more sequence, and it appears in the journal Economic Inquiry, 2012. It's very short, 2 pages. Suppose you have 2 players, like say tennis, for example, and I suppose that to begin with, if you begin, you have some sort of advantage. I mean, either real advantage or psychological advantage or whatever. So if people take turns, they are going to play A, then B, then A, and B, then A, and B, and so on and so forth, up to some point. And you see that A has an advantage by beginning, and so this advantage is never compensated, so to say, for Mr. B or Mrs. B. So you can think that it would be more fair, instead of alternating A and B, then once you have an AB, afterwards you have a BA. so that somehow you compensate the advantage of A. And if you do that, you get ABBA, 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 and so on and so forth. It looks a little bit more fair, and actually it happens in real life. In tennis, if you know what happens when you have a tie break, this is exactly the way people play. Of course, you guess that you might go further, and if you think that ABBA is not very fair, you have the idea of, after ABBA, putting BAAB, and then you have a sequence of length 8, I mean a word of length 8 that you just that is going to be the period of an infinite sequence, which looks a little bit more fair. In the same direction, there is an interesting paper by Cooper and Duttle called Greedy Galois Games, with probabilities and things like this, going a little bit further into this idea, which I am going to make more precise yet. Okay, you have a sequence of zeros and ones. You remember that Thue was a number theoretist, and you say, okay, can we do something in number theory, whatever this means, with this PTM sequence, for example, but the transcendence of the sequence, actually the transcendences of the sequence. Okay, for example, take the sequence AN, 0, 1, 1, 0, 1, and so on. Look at the formal power series sigma of A n x to the n. Consider it over z over 2z of x, and ask whether what you obtain is algebraic or transcendental, which makes sense. You have a field and so on and so forth. And you know very well that the sequence is algebraic. For this particular sequence, it's very easy to prove. And of course, there's something more general behind, which is the Cristol theorem or Cristol, Kamen, France, and Rossi theorem that says precisely, give a precise relation between algebraicity and automaticity. But if you replace the field by, let's say, z over 3z, what happens is you lose the algebraicity, you get something which is transcendental, and this is essentially a mixture of Cobham and Cristol. Of course, you can also think of the an to be digits of a real number after the decimal point, binary point. For example, take an integer b, which is at least equal to 2. Look at the real number summation of an divided by b to the n, where an is still 0, 1, 1, 0, and so on and so forth. And you can prove that this number is transcendental. It was the general theorem of Mahler proving that. A simple proof was also given many years later by Decking. And now there is a quite general result by Adamczewski and Bugeaud, saying that each time you take an automatic sequence and you make the same thing, which is namely look at a real number, having this sequence as digits, whatever the base is, integer base, or maybe piso base, it works also, I guess. Then you get either a rational number or transcendental number. You never get root 2. I mean, you never get an irrational algebraic number. So rational or transcendental is kind of duality. Now take the continued fraction. Well, you have zeros, so it's not quite permitted to take this continued fraction. So replace, for example, add 1 instead of 0, 1, 1, 0, take 1, 2, 2, 1, or any a and b different, and look at the sequence a, b, b, a, b, and so on and so forth, where the a and b are distinct integers. And what you get, what you obtain is something which is transcendental of a Q. You know, there is an old question or conjecture saying that if you take an algebraic number which is not quadratic, so of degree at least 3, then its continued fraction expansion cannot have bounded partial quotients. And here you construct very easily a transcendental number just by taking the stupid continued fraction with bounded partial quotients. Okay. Now you can ask what happens conversely. In other words, you take for example, polynomials. You put these polynomials as a Morse sequence, A, B, B, A, B, A, and so on. And suppose you are in characteristic 2. So this continued fraction corresponds to a power series in 1 over x, mod 2 again. Okay, let me call this psi of A, B. Of course, A and B are distinct. And what can be said about this sequence, the power series? And the answer, maybe surprising, is that this series is algebraic, whatever A and B are. A and B are distinct. But not only it's algebraic, but also it is of degree 4. Okay, in the case where the polynomial said small degree, which is degree at 7, it was proved by Yining Hu and Guanyu Han in 2020. I mean, this is going to appear in Acta Arithmetica, or maybe next year, because Acta Arithmetica is very slow, as you know. And actually, in the case, it's also true. It was proved quite recently. The preprint was appeared on the archive this morning. I mean, in France at least, where they prove exactly this result on the top of the slide. You always have something algebraic and always of degree 4. And the idea of Yining Hu and Guanyu Han was to obtain the minimal polynomial of psi A B. And what Bujoux and Han did is to guess the polynomial in all cases and to check that he was right and it was a degree 4 and so on and so forth. Yeah. That's pretty surprising. I mean, being algebraic is a little bit surprising because remember, it was transcendental if you take something with numbers. And also, what is also surprising is that degree is the same, whatever A and B. Even if A and B have enormous degree. I mean, that's amazing. Okay, two Morse and Von Koch. You know the Von Koch curve, sometimes called the Snowflake Curve. And if you go to a paper of Coquet in '83, a summation formula related to the binary digits in Invenciones, you have this picture. I think the name Von Koch is not used explicitly. I'm not sure. And this is obtained. What he is interested in is you take the Morse sequence with values, say 0, 1, 1, 0, 1, so on. And you look at the sequence on every third term. So you look at A0, A3, A6, A9, A12. That's pretty surprising because A0, 3, 6, 9, 12, 15, 18, you get 0. For 21, you get 1. So you have the impression that somehow you have more zeros than ones. Of course, it's not true because at the limit you get half of each. The density, the frequency is the same and it's equal to half, which can be proven, of course. But to have this impression of having more zeros than ones, you replace 0 by +1 and ones by -1, and you look at the symmetry function, huh? So the summation of -1 to the an for n smaller than capital N. As I said, this is small of capital N, but it can be proven that this is between 2 positive constant times capital N to the log 3 over log 4, the famous log 3 over log 4, which means that this has somehow tendency to be positive. I mean, a tendency that you have more zeros than ones, although this is not true at infinity. Okay, there is a paper by Decking at the same time, about the same time, 82, 83, where he proved the same thing. And recently, Ma and Holdenov, relatively recently, 2005, they rediscovered the results and without knowing and without citing the paper of Coquet and Decking. And Gensho Skordev and myself wrote a paper in 2007 to say, hey guys, this was well known before you. My ex-doctoral student Yao Yang Li did something 2021, you can guess. I'm not going to again to enter details, but you have you can make a generalization of Vancouver curve. You can make many generalizations of the Thue Morse sequence, and of course you can mix those things. I see some more pictures, but okay, maybe we could call this a picture. Okay, some more pictures. For example, in the paper by Decking, you have these 4 nice pictures. Top left, you have the usual Vancouver curve, except that usually it's a six branch star, and you have all these things together to make a famous snowflake. And you have modifications or generalizations. And I mean, okay, the best is to go and see the paper. Maybe I forgot to say something about Coquet. If you are interested into this A0, A3, A6, and so on, you can have the idea to study the symmetry function of J. Let me call J a cubic root of 1. So symmetry function of J to the n a n. And if you do this, you get this kind of thing. Actually, if you want more pictures and more theory in a similar vein, you know, this is it was called Logo in the old days, and then there was a Turtle program or something like this. It's to train people to programming. I mean, young people, very young people to programming. You move from a unit, and then you turn from an angle given by some a priori sequence, then another unit, and then you move by another angle, and so on and so forth. And if you do that, you can get nice results. I mean, nice pictures, and sometimes nice results. The 2 papers I have in mind are a paper by Decking and Mendes France in the journal für die reine und angewandte Mathematik in 1981, Uniform Distribution Mode 1, the geometrical viewpoint. And soon after, a paper by Jean-Marc Desouillet, Geometric aspect of veil sums, published in some volume of the Banach Center publications. And actually, there are many papers. For example, if you look for the word curlicues, you get another bunch of nice pictures and or nice results. Okay, I'm now going to make a quick allusion to what is called semi-2 systems. I'm not going to define them, just saying that these sort of restricted kind of writing systems, and they were introduced again by our friend Axel Thue in 1914. Probleme über Veränderungen von Zeichenreihen nach gegebenen Regeln, again in German, again in the Scandinavian Journal. Okay, I'm not going to say anything about this. Oh, yeah, something. There is a translation of this paper. If you feel lazy to look at it in German, there is a translation by Popper that you can find on the archive. And the translation is 44 pages long. Okay, many people were interested in this semi Thue systems, and in particular, Gérard Huet. Gérard Huet, for example, he published a paper in the Journal of SEM in 1980, Confluent Reductions, Abstract Properties and Applications to Term Rewriting Systems. Why did I cite Huet? Of course, he was one of the, not the first probably, but one of the first people interested in this kind of systems, but also for another stupid reason, that if you take Huet and you take the T at the end of Huet and you put it at the beginning, you get Thue. You know, playing with words like this, I mean, in a certainly more literary way, is very popular in France. Somebody, Manon, mentioned motus and sutum. And I mean, the literary part of that is the so-called Oulipo movement, ouvroir de littérature potentielle. And this is a gathering of essentially French-speaking writers and mathematicians who seek to create works for using constraints in their writing techniques. It was founded in 1960 by Raymond Queneau and François Le Lyonnais. And one of their famous members is Georges Perec. And you probably know that Georges Perec wrote L'Hypogramme in French, L'Hypogramme being a novel, I mean, can be one page, it can be a novel. In this case, it's a novel where you try not to use some fixed letter. Of course, if you want to write a novel without letter Z or without letter W in French, it's not a big deal. But the tour de force of Perec was he wrote a book called La Disparition, without any E, and E is the most frequent letter in French. Interesting enough, this book was translated into other languages, where of course the most frequent letter might be something else than E. And so it was another tour de force to translate it in different languages. And, you know, interestingly enough, Georges Perec was born on March 7th, 1936, again, this 7/3. Okay. I can make a first stop here, and thanking you, but maybe I'm going to say a little bit, a little thing, one or two more little things. The first thing which is not written on slides is about music. You probably know that my favorite quote about music is, of course, there is no relation at all between math and music. And every time I say that, there is someone in the audience saying, so what? What about the scales? I say, come on, you're not going to say that scales are music, are you? But still, I mean, if composers want to use some mathematics to compose music, I mean, they can, of course. I'm not going to forbid that. I can even cooperate with them, which I did sometimes. And the Moore sequence was used in different contexts for this. And in particular, there is a journal called Journal of Mathematics and Music, where a sort of recent paper, I have not the reference on hand, used the two Moore sequence both for scales and for, how is it, for a keyboard or something like this. Some curious way of using the Moore sequence. So in this Journal of Music and Mathematics, you can certainly find other occurrences of the two Moore sequence. There is also a paper, a journal called Journal of Mathematics and the Arts, where you get this time. What I found there for the moment is papers about the two Moore sequence used in painting or in pictures or things like this, and not in music yet. But maybe I missed some of it. Okay, so let's go back to the very, very last part, probably, of what I'm going to say today. Recall that Thue wrote something like, further removed from usefulness or practical application, the more important. We have seen that the semi-Thue systems were essentially introduced by Thue, even if they were not used in computer science in 1914. But there is something else. There is a programming language called Thue, and Wikipedia says the following: this is an esoteric programming language invented by John Colacioa in the 2000s, and it's a meta language. We used to define and recognize type 0 languages from Chomsky hierarchy, because it's able to define languages of such complexity. It's also very complex itself. Okay, and this is called this is based on the writing system, which is a semi-Thue grammar, of course, named after this Norwegian mathematician, our friend Axel Thue. Okay, this time I'm going to stop there and wait for you possible questions about two Moore sequence or some sort of unusual occurrences in the sequence. Thank you very much. Vielen Dank. Merci. Arigato. Xie.
Okay, let's thank Jean-Paul for his talk. And let us see if there are any questions. If there are, you can just unmute yourself and ask directly, or you can type into the chat.
Is there a question by Christophe?
Hello. Bonjour, Jean-Paul.
Salut, Christophe.
You hear me, yes.
Yeah.
I just wanted to mention something about history. As far as I remember, it was Jean Berstel who introduced the work of Thue at the end of the, to the community, I mean, community of Combinatorics and words, let's say, and at the end of the 70s. Is this true, or do you agree with this statement, or?
I think it's true. At least Jean made a translation of these fundamental papers by Thue. So probably before him.
This translation was made much later. I mean, the translation appeared here in Montreal, edited by Srečko in the 90s, perhaps, or the 80s. But but Bercel already worked on Thue sequence in the 70s, and so
I think the most ancient work of Bercel, published work of Bercel, I'm aware of, is at the end of the 70s or very beginning of the 80s. For example,
78.
Sorry?
78.
78. Do you allude to the paper in the journal in the Séminaire de Bordeaux, or maybe something else?
Something like this, yes.
Okay. Yeah. So now it's plausible that he was the first to introduce the work of Axel Thue to this community, as you said, of combinatorics on words. I think that's quite plausible. I mean, I don't know of anybody else. So, I mean, before him.
Well, there was this paper in 1967 by Headland entitled "Remarks of the Work of Axel Thue on Sequences," in which he pointed out Thue's papers and pointed out that the results had been rediscovered. So that was a little bit before, but I'm not sure that counts. So I don't know how much Headland's work was known to.
Yeah, actually, depending on what you call the community.
Yes.
So I'm not sure that the paper of Headland was very, very well known among computer scientists. So who knows? I don't know. Anyway, thank you for the reference. Thank both of you for the references.
Jean-Paul also was too polite to mention that one of his former students, Olivier Salon, is a member of Oulipo.
Yeah, that's true.
Do you have any other students who are members of Oulipo?
Not that I know, but interestingly enough, he finally abandoned completely mathematics, his position and so on. I mean, just Oulipo, and that's it. Oh, there is another contemporary mathematician, but nothing to do with me, so to say, who is at Oulipo. And okay, sorry, but her name is gonna come back to my mind in a. Sorry about that. I mean, okay, in 2 minutes, I'm going to remember her.
I was also impressed that you arranged for one of the fundamental results you're talking about to be published this morning. So on the archive, how did you manage that?
I must confess that I got a preprint before. Yeah, Jan Bijot sent me a preprint like maybe 1 or 2 weeks ago, and by chance I found this the thing in on the archive today. Yeah.
Okay, are there any other questions?
Just a comment more. I like, thank you for the talk, by the way. And I like the two comments by Thue, about the usefulness. I like this. The first one I knew because I remember Bercel quoting it, but the second one is more precise even. And I like it. It remembers me, a friend of mine, a mathematician too, who said to me perhaps 15 years ago, he said something like, I'm just saying it differently because my English is not very good. He's something like the less it's useful, the less research is useful, the better is it for the planet. We could say that.
But by the way, there's an interesting question about being good for the planet. To give a talk by Zoom, instead of making a gathering of people physically coming to some conferences, is that better? Or
you ask me, or I don't know.
I mean, I ask in general. I mean, no, I ask in general. You know, I was convinced it was better, but apparently, I mean, it looks like we are using a lot of energy and rare materials and so on and so forth. So it's not clear whether, I mean, it's certainly less tiring for mathematicians to travel, probably less interesting as well. But about the planet, I'm not sure. Yeah, something that I didn't forget, I did not mention, I forgot to mention in the talk is, can you obtain sort of random or pseudo-random sequences with a two-more sequence? Of course, the two-more sequence is not random at all, whatever your definition of randomness is. But how far, I mean, how far can you use this sequence to obtain a random sequence? And for example, if you take the two-more sequence and you restrict the indices to be squares, so you take U0, U1, U4, U, and so on, U9, and then every block occurs. So it's more random than the usual the usual two-more sequence, but it's probably not random, not that much random. So the question is how much pseudo-random you can do. You can make the more sequence if you modify it somehow. Of course, I don't define what somehow is.
Okay, are there any other remarks or questions? Okay, if not, then let's thank Jean-Paul once again for this